Part 2 of our notes today is on the kinetic molecular theory, which is abbreviated KMT. The kinetic molecular theory is a theory that describes the behavior of a perfect gas, if gases were to behave perfectly. So how you should think of a gas, in other words. So the first part of the theory, there's 5 parts of it, by the way. The first part says gases are composed of particles. These particles could be molecules or they can be atoms. So you could have like a molecule of O2, oxygen gas, or you might have an atom of helium gas. You should think of these particles as small hard spheres. They have almost no volume compared to the volume of their container. The second part of the kinetic molecular theory says these particles are in constant random motion. So since they're in constant random motion, they're going to collide. They will collide with the walls of the container, and that's where the gas pressure would be created by the collisions with the walls of the container. And they also can collide with one another. Now, these collisions are considered to be perfectly elastic. Now, what that means, the phrase perfectly elastic, is that no kinetic energy is going to be lost as a result of their collisions. Instead of losing kinetic energy, they transfer their energy. So the energy is transferred from one particle to another. The next part of the kinetic molecular theory talks about that kinetic energy. It says that the average kinetic energy is directly proportional to the temperature in Kelvin. Kelvin is our SI unit of temperature, and it is the only temperature scale that does not have any negative numbers. So in all of our gas laws that we're going to be doing in this unit, we have to remember if there's a temperature value that we're plugging in, it has to be converted to Kelvin. But the average kinetic energy is directly proportional to the temperature in Kelvin. So what does that mean? Well, it means gas particles that, say, have a temperature of 200 Kelvin are going to have twice the kinetic energy as gas particles that would be at 100 Kelvin. So directly proportional means if the temperature is doubled from 100 to 200, the kinetic energy will also be doubled. One goes up, the other goes up. If the temperature goes down, the kinetic energy goes down. The last part of the kinetic molecular theory states that there is no attractive or repulsive forces between the particles. So if they collide with one another, they will transfer their energy and bounce off of one another. But they're not going to attract to one another and stick together, say like a magnet. And they're not going to like repel one another necessarily. If they happen to collide with one another, they will simply bounce off and ricochet off and continue on their merry way. So that's the 5 parts of the kinetic molecular theory. Now remember, the kinetic molecular theory describes the behavior of a perfect gas. And perfect gases are referred to as ideal gases. Think about living in an ideal world. Sometimes people may be described as they live in an ideal world, which means it's a perfect world. That would be great if the world was perfect, but of course we know it's not. Nobody's perfect, but sometimes we can behave perfectly if we need to. So that's how I want you to think about these gases. The kinetic molecular theory describes a gas that is on its very best, most perfect behavior. So I say that because we're going to contrast real and ideal gases here. The kinetic molecular theory applies only to ideal gases, and we will always assume our gases are ideal gases in all the gas law problems that we do. I need you to understand, though, that a true ideal gas does not exist. So again, remember, ideal gas means perfect gas. Just like there is no perfect person, there is no perfect gas. But as I mentioned, we can behave perfectly if we need to for a short amount of time. Well, gases can behave perfectly under specific conditions. There's 2 ways that real gases differ from ideal gases. The first way is that real gases really do have some attractive forces between the particles, or intermolecular forces, due to their polarity or the ions that may be present. Real gases also have definite volumes. Keep in mind, it's a state of matter, and one of the criteria for matter is anything that has mass and takes up space. So we know that since it's a state of matter, it has to have volume. But the kinetic molecular theory assumes that they have no volume. Well, what it is the particles are so far apart compared to the volume of their container. Their volume is so tiny we can neglect it. It's said to be negligible. Now, there are certain conditions under which real gases behave as ideal gases. So, when our gases behave perfectly, in other words. And those conditions happen to be high temperatures when it's really hot. That means they're moving really, really fast, have a lot of kinetic energy. And low pressures. That means they have lots of room to move around. They're not all cramped together, they're able to spread out. So, under the conditions of high temperatures and low pressures, gases do behave ideally or perfectly. Well, this just happens to be the very conditions that our world that we live in. We live in a high temperature, low pressure container. Our gases that we come in contact with on a day-to-day basis. We have hot temperatures and low pressures, and those are the perfect conditions for gases to behave ideally or perfectly. So that's why we can assume our gases are perfect gases. In our next lesson, we're going to talk about pressure and the units of pressure. So I just want to talk a little bit about how we measure pressure. We use a barometer. Now, the pressure is defined as the force divided by the area, so force over area. And so the very first barometer was designed or invented by a man by the name of Evangelista Torricelli. Now, Torricelli was an Italian scientist. And Torricelli took a container and put mercury in it, and then had this tube that he inverted. And notice the tube is marked off, and the measurement unit here is millimeters. And so what happened was he was able to measure, like when the air pressure got really big, it would push down on the level of mercury in the tube. I mean, in the dish, and it would therefore make the level of mercury in the tube rise. Kind of like when you sit in a tub of water, the water rises; it's displacing it. So you would be able to measure the pressure in millimeters of the mercury. Whenever the atmospheric pressure releases or is little, it lifts up. Out here, the pressure doesn't push down as hard, so that means that the level of mercury in the barometer would fall. So the very first barometer was invented by a man by the name of Torricelli, and that's going to be significant in our next lesson.